So in this lecture, we are going to cover the formal mathematical definition of morphological erosion of an image with a structuring element. And just like we did for dilation, we are going to give a formal definition of erosion operation using the sets and basic set operations. So again, assume that we have an n cross n operator which contains our structuring element, and our structuring element is defined as a set ST, which is a set of all pixel coordinates in Z square such that T of P is equal to 1. We have an image that we want to erode with our structuring element by applying this operator which contains our structuring element. So we can define a set corresponding to our image. So we have a set Si, which is a set of all pixel coordinates Q in Z square. So Q is again a set of all pixel coordinates. It's a two-dimensional integer vector such that I of Q is equal to 1, where I is our again binary image, and T, the operator, is also binary. So we know that the erosion of this image with this operator is going to produce a binary image R as an output, which has 1 at all locations I, j, such that the structuring element fits image I at I, j. And any location where the structuring element defined contained in this operator doesn't fit the image will have zeros at all such I, j. That is, T does not fit I at location I, j. So again, we can define a set SR, which is a set of all coordinates set of all coordinates Q, because we typically use R for rows, set of all coordinates Q in Z square such that R of Q is equal to 1. And this set is a set of all pixels. This set is also equal to set of all pixels Q in Z square such that T fits I at Q. So these are both, so this is the set SR. So we perform this operation, we get set SR, and to get the resultant image, we just set R of Q is equal to 1 for Q belonging to set SR. And again, as we did in the morphological dilation, we can just expand everything in terms of set operation, basic set operation, the subset operation, and we'll see an example as well of this, which we can just expand everything. So we'll just write all the sets together. 1, we have set ST, which is a structuring element. It is a set of all coordinates P such that T of P is equal to 1. We have set Si, which is a set of all q in z square such that I of q is equal to 1. So we have set SR, which is obtained by eroding the image I with the structuring element ST. So this set SR is given by, in terms of basic sets operation, it's going to be a set of all pixel coordinates T belonging to Z square such that we'll just use P over here because it would be confusing to use T because we have T over here. So just to make the notations clear, we'll use P over here, P again over here. So it's a set of all coordinate P in Z square such that ST translated by P is a subset of our set Si. So this is the definition of set. This is a formal mathematical definition of our set SR obtained by eroding the image I with a structuring element ST by applying an operator T that contains our structuring element. So basically, if we have an image and we apply the operator to erode the image which contains our structuring element ST, so it will give us the set SR, which is a set of all coordinates P in Z square such that ST translated by P is a subset of set Si. And now to obtain the resultant image, we just set R of Q is equal to 1 for all Q in set SR. And we set RQ to 0 for Q not belonging to set SR. So this is the erosion operation purely defined in terms of sets and set operations. So notice that in dilation we took a reflection of the set, but we do not have this reflection in erosion, and that's why erosion is analogous to correlation and dilation is analogous to performing convolution with the operator T. Whereas the operation that the dilation uses is a hit operation and the operation that erosion uses is a fit operation. So we'll consider a numerical example to give you again an understanding, a physical understanding, a graphical understanding of what these operations look like and how do we verify that this is the correct result. Just like we did in dilation, we are going to consider a graphical example. So assume that we have an image. Now assume that this image looks something like 1 1 1 0 1 0 1 1 1 0 0 0 0 1 1 1 1 0 1 1 1 1. So, and let's suppose we erode this image with structuring element, let's say something that is easier for us to perform over here. So we just select an easy structuring element. Let us select a vertical structuring element. So we have 0, 0, 0, 1, 1, 1, 0, 0, 0, the same as we used in dilation. So again, our set SI, so this will give us a resultant image. Again, so this is our coordinate 0, 0, and to perform erosion, we just append this image with row at the top, column at the right, row at bottom, and a column on the left. So this is our pixel coordinate 0, 0, and this is our pixel coordinate -1, -1. So to perform the erosion, we will have to add rows and columns of all ones to perform erosion on these boundary pixels. So our set SI, original set, so ignoring, so we'll just by default assume that we have all these elements as well in the set, but just consider the elements that are the coordinates in this image that are true. So our set SI is given by a set of coordinates. So here we have 0, 0, here we have 0, 0, 0, 1, 1, 0. This we have 2, 0. Here we have 4, 0. Similarly, we have 1, 1. Here we have 1, 2, 1. We have 3, 1. Then we have 3, 2 and 4, 2. Then we have 4, 0, 4, 1, 1, 4, 1, 3, 0, 1, 2, 3. We have 0, 3. We have 1, 3. Then we have 3, 3. Then we have 3, 4. 4, 3. And then we have 0, 4. We have 1, 4. We have 2, 4. We have 3, 4 and 4, 4. And assuming that we have these coordinates, so this is -1, 1, this is 0, -1, this is 1, -1. So we have all the negative coordinates as well. These are going to be the part of this set as well, but we have not written them explicitly. And we have ST defined as all coordinates. So this is coordinate -1, -1. This is 0, -1. So we have 0, -1. We have 0, 0. And we have 0, 1. So now when we perform erosion over here, then the resultant image that we would get is, so if we place this operator centered on this pixel, we'll get fit operation will result false due to this 0. So it's 0. Here it will return true. So we have 1 over here. Here again it would be true over here. So we have 1 over here. In this location we'll get false due to the center pixel. We don't need to check any other pixel. So we'll get false, and again when we place it over here, we'll get false due to this pixel. So we have 0. Similarly here we have 0, over here as well due to this pixel. We have 0 again for this one due to this pixel. We have 0 over here due to the top pixel, and we have 0 here by default. Here for these three elements we have 0, and then here we have 1, and then here we have 0. So 1, 0. Then here we have 0, 0, 0, 1, 1. 0, 0, 0, 1, 1. Then we have 1, 1, 0, 1, 1. So we can compute our set SR. So this is our resultant image R. So we can define our set R to be, so this is 0, 1, sorry 1, 0. Here we have 2, 0. Then we have 0, 1, 2, 0, 1, 2, 3, 3, 2. Then we have 4, here we have 3, 3 and 3, 4. 3, 3 and 4, 3. Then we have 0, 4. We have 1, 4. We have 3, 4 and 4, 4. So this is the graphically we just did erosion of this image with this structuring element, and this is the result we get. So we have just defined these sets by graphically looking at our resultant image. Now let's check whether this formula holds true or not. To see how the formula works, we'll now just check element by element. So our mathematical formula says that set SR should be a set of all coordinates such that ST translated by P is a subset of SI. So let's check whether this holds or not to intuitively understand erosion. So let's check our first coordinate 1, 0. So let's translate our set ST with the first element in set SR 1, 0. So by translating the set with 1, 0 will give us 1, -1. It will give us 1, 0 and 1, 1. We'll just add 1, 0 to all the elements over here. So we see 1, -1 is a part of set SI because this is 1, -1 coordinate. Although we have not, we remember earlier we mentioned that all the negative coordinates are part of the set SI, but we have not written it. Otherwise it will just become too long. So 1, -1 is a part of this set because this is location 1, because we appended a row and column. So this checks out. Now let's check 1, 0. So we see 1, 0 is part of our set SI. Now let's check 1, 1. So 1, 1 is again part of our set SI. So this 1, 0 holds true. Now let's translate our set with 2, 0. So 2, 0 will give us a new set 2, -1. Add 2, 0 to this, so we'll get 2, 0 and we'll get 2, 1. So for this set, translated set to be a subset of SI, all these elements should be found in our set SI. And 2, -1 is found by default, so this is our coordinate 2, -1, which is in set SI. Let's check for 2, 0. We have 2, 0 over here. Let's check for 2, 1. We have 2, 1 over here. So the translated set is again a subset of set SI. So this one also holds true. Let's check for 3, 2. So if we translate our set with 3, 2, we will get a new set 3, comma 1. This will become 3, comma 2. And this will become 3, comma 3. Now let's check whether all these elements are in set Si or not. So 3, comma 1, we have 3, comma 1 over here. 3, comma 2 we have over here. And 3, comma 3 we have over here. So this one also holds true. Let's check for 3, comma 3. With 3, comma 3 we get set of 3, comma 2, 3, comma 3 and 3, comma 4. So 3, comma 4 is over here, 3, comma 3 is again over here, and 3, comma 2 is over here. So this checks out. Now let's check for 4, comma 3. So with 4, comma 3 we get translated set of 4, comma 2, 4, comma 3 and 4, comma 4. So 4, comma 2 is present, 4, comma 3 is present, and 4, comma 4 is present. So this checks out. Let's check 0, comma 4. So with 0, comma 4 we'll get a new set. This would be 0, comma 3. We'll get 0, comma 4 and 0, comma 5. So 0, comma 5 exists by default. So this is our coordinate 0, comma 5. So this checks out. Let's check for 0, comma 4. So 0, comma 4 is part of set Si. Now let's check for 0, comma 3. 0, comma 3 is present in set I. So 0, comma 4 also checks out. Let's check for 1, comma 4. So with 1, comma 4 we have translated set 1, comma 3. We have 1, comma 4 and we have 1, comma 5. So 1, comma 5 is present by default because we appended. So 1, comma 5 is part of this set. Let's check 1, comma 4. It is present. Let's check 1, comma 3. Presents true. This checks out. Similarly 3, comma 4 will get translated set as 3, comma 3, 3, comma 4 and 3, comma 5. So 3, comma 5 is present by default. So this is our 0, 1, 2, 3, comma 5. Let's check 3, comma 4 and 3, comma 3. 3, comma 4 is present, 3, comma 3 is also present. So 3, comma 4 also checks out. Let's check 4, comma 4. So 4, comma 4 will give us translated set 4, comma 3, 4, comma 4 and 4, comma 5. So 4, comma 5 is again present by default because we appended. So this is 4, comma 5. 4, comma 4, let's check for it. 4, comma 4 is present in the set. 4, comma 3 is present in the set again. So this also checks out. So we can see we just have verified the mathematical definition of erosion in terms of sets and set operations, and we also checked it out graphically, and this all adds up together. So we can write, we can put all these together neatly again, and we can just define all the operations neatly in terms of set operations. So we have an image I. We want to erode it with an n cross n operator which contains our structuring element. So the first step is to define the set ST, which is our structuring element. So it's a set of all coordinates P in Z square such that T of P is equal to 1. Second, define set Si, which is a set of all coordinates Q in Z square such that I of Q is equal to 1. define the result of erosion of an image with this structuring element is going to give us a set SR, which is a set of all coordinates lambda in Z square, such that set ST translated by lambda is a subset of our set SI. And we just verified this as well via a numerical example and checking each of the individual elements and verified this operation. And the last step is to compute the image R, which is obtained by setting all the pixels at location Q to 1 for all Q in set SR and is equal to 0 for all Q not belonging to set SR. So these operations define the morphological erosion operation formally mathematically, purely in terms of sets and basic set operations. So that covers our discussion of the morphological erosion.